Hi, welcome back to this OS academic series. And in today's session, today's lecture, we are going to look into another scheduling algorithm, which is called priority-based scheduling. So, boys and girls, this is lecture number 9 in the series of operating system. And this is the usual, the disclaimer. And this is the topic. So, therefore, the scheduling technique is called priority-based scheduling, and this is a realistic one, which is essentially used in many contemporary operating systems also. And in real-time operating systems as well, we use the scheduling mechanism, which is called priority-based scheduling. As you know, priority is one of the attributes of a process. Priority basically indicates the level of importance of the process, how important the process is among all the processes in the system. And generally, priority is computed at the time of creating the process, and it is computed by means of a function taking into consideration several parameters like type of process, size of process, the number of resources the process is using. So based on that, we can take some weightage of these parameters or metrics and compute the priority as an integer value. So here, if you see the notes, priority generally is a number that is an integer associated with each process, and the processor is allocated to the process with the highest priority. And when it comes to the matter of saying highest priority, we have conventions here. Which number should be taken as highest priorities? In some convention, they say smaller integer is highest priority or larger integer is higher priority. So that's only a matter of convenience, matter of convention. Typically, when a question is asked, generally they specify in the question what convention is to be followed. That is, the higher number is higher priority or smaller number is higher priority. That's not so of point of concern. The modality of operation, the mode of operation of this. So this is a selection criteria. Priority number is a selection criteria. Okay. And the mode of operation of the scheduling mechanism, mode of operation is essentially can work in both preemptive or non-preemptive mode. And let me also tell you the fact that the basic approach of working of this algorithm or the working mechanics of this algorithm is exactly like SJF. We have in SJF, we look into the burst time. Here we look into the priority. And in fact, SJF is a type of priority where we are giving the priority to that process which is having the least burst time, right? The process having the least burst time is given the highest priority. So in fact, SJF can essentially be treated like priority-based scheduling. So the way it works is exactly like SJF, so we shouldn't have much problem here. So SJF is priority scheduling, where priority is the inverse of the predicted next CPU burst time. Of course, the problems and solutions we should see at later point of time. Here is a simple example to indicate the working of priority-based scheduling. Here I am assuming no arrival times. In fact, it means that all the processes have arrived at the same time. That is a convention we have already been seeing several times. That means if arrival times of the processes are not given, we essentially assume all processes are available at the same time 0. So boys and girls, this is a set of 5 processes. Their burst times are as follows, and these are the priorities. So at time 0, we have all these processes. So which process is considered to be the highest priority? So here we follow lower number is higher priority, higher number is lower priority. So naturally, if you look at the Gantt chart, we are going to schedule P2 first. P2's burst time is 1 unit. So it runs from 0 to 1 and complete. After that, the next highest priority is P5. So P5 will run next, taking burst time of 5, 1 plus 5, 6. And after that, the next highest priority is P1. P1 is going to take 10 units. So 6 plus 10, 16, it completes. Thereafter, P3 need 2 units. So 16 plus 2, 18. And finally, P4 taking 1 unit of time and complete. So that's a very simple aspect. And like SJF, we can even have here the conflict or tie breaking. That means in case if multiple processes have the same priority, what are we going to do? So as I have been telling you, there is no specific general convention or generality with regard to that. Whenever there is a tie or conflict among processes with regard to selection criteria, we are going to follow some convention which will be specified. Like in SJF, I said you follow arrival time. Whichever process arrives first should be given the priority, in case if burst times are same. But sometime what happens, arrival time can also become same. So in that case, you can resolve it with process ID, whichever process is having lower process ID. So typically we can follow the same convention here as well for priority. That means if multiple processes are having the same priority, then we look into the arrival time. We try to resolve through arrival time. But if arrival times are also same, then we will look into lower process ID. And do remember that no two processes can have the same lower process ID, or no two processes will have the same process ID. So it definitely will get resolved with process ID. So what we do is I will take a general data set with different or jumbled arrival times, and then we'll make a trace with regard to preemptive and non-preemptive priority. Say for example, this is a priority of the process, and let's say this is a process number, and I will take arrival time and burst time. So we'll take some number of processes, 5 processes. Let's say their arrival times are something like this, and let's say some burst times are also there, 10, 5, 8, 6, 3. All right, and then we'll take some priorities here. Let's say this priority is 8, this priority is 4, this priority is 2, this priority is 3, and this priority is 1. And we follow the same convention that lower number is higher priority, higher number is lower priority. So following that convention, there is highest priority and the lowest priority. So when I prepare the Gantt chart using non-preemptive approach and preemptive approach, so how does it look like? Let's see here. So I'll typically prepare the Gantt chart for both. Okay. So let's say this is the Gantt chart for non-preemptive priority. Okay, non-preemptive priority. So let's prepare the Gantt chart. So we'll say this is the CPU, time starts at 0. So at 0, we have typically only one process, P1. So I don't have any choice other than scheduling P1, and since it is non-preemptive, it is going to take all 10 units, burst time 10, and complete. And by this time, remaining all processes have made their entry. So among them, the one having the highest priority is P5. P5 need a burst of 3 units, so it is going to complete at time 13. This will be followed next by P3. P3 need a burst time of 8 units. So 13 plus 8, 21. Is it not? And after P3, which is having priority level of 2, I will schedule P4 next. P4 is having priority of 3 and burst time of 6. So therefore it is going to finish 21 plus 6, 27. And finally thereafter we are going to take P2, which is the last highest priority among them. So P2 needs a burst time of 5 units, as you see here. So 27 plus 5, 32. So boys and girls, this is the Gantt chart that is going to be for you can say preemptive, non-preemptive priority based scheduling. Non-preemptive priority based scheduling. And once you compute this, once you draw this Gantt chart, you can essentially compute average turnaround times, average waiting time, whichever performance metric you desire. You can always make a computation of it. Okay. So now the question is, how does this algorithm work in preemptive mode? Same data set in preemptive mode. Preemptive priority based. So when preemption happens, or how do preemption occur, that is what we have to see. So what I do is I will prepare the Gantt chart. Okay. This is priority 1. Fine. So let's draw the Gantt chart now for preemptive priority based scheduling for the same data set. See here on board. CPU 0. Time moves in forward direction, as I have been telling consistently. Is it not? Now look at this. At time 0, I don't have any choice other than starting with P1. So P1 is going to run till time 1. Because at time 1, we are going to receive a new process P2. So therefore, now we compare the priority of P1 and that of the priority of the new process. Priority of new process P2 is 4, 4 is less than 8. So that means it is higher priority than 8. Because I am following the convention, lower number, higher priority, higher number, lower priority. So therefore, P2 has high priority. So essentially, we are going to have preemption here in favor of P2. This is called preemption approach. P2 is also going to follow the same paradigm. It is going to run till the arrival of new process. New process arrives at time 2, namely P3. P3 is having priority 2. 2 is greater than 4. 2 is lesser than 4 means high priority. So P3 will preempt P2. So P2 get preempted in favor of P3. P3 is going to run, look at this, P3 is going to run till the arrival of new process. New process arrives at time 4. Please follow carefully. At time 4, we receive P4. But the priority is 3 and 3 is not less than, 3 priority is not less than running process P3. That means new process is not having a better priority or higher priority. It is having lower priority. So no preemption. And in fact, P3 will continue till the arrival of next process. Next process arrives at time 5, so it has run for 3 units. So P3. Its balance is still 5. Its balance is still 5 because its burst time is 8. So it has run 3 units. Now, boys and girls, at time 5 we receive P5. P5 is having priority of 1 and that is superior, that is highest. Now preemption will happen in favor of P5. And P5 being the highest priority is going to run all its burst 3 units 8. So P5 is over. After P5, we will see the remaining processes who are still pending to complete their execution, and among them the one having the highest priority. Who is having the highest priority? P3 with priority 2. Its balance, earlier you see P3 has run for 3 units, 2 to 5. So its balance is 5. So now P3 is going to run for its balance 5 units. 8 plus 5, 13. So P3 is also over. So you can mark P5 is over, P3 is over. Next highest priority is P4 with a priority of 3 and its burst time is 6 because no new process is going to come, so therefore we are going to run till completion. So P4 completes at time 19, so P4 is also over. Now we have P1 and P2 and among them the highest priority is P2. Remember, P2 has run for 1 unit earlier, 1 unit, so its balance is 4. So P2 is going to run for 4 units, 23. Is it not? 23. So P2 is also over. And then finally we have P1. P1 has a balance of how much? You check, P1 has earlier run for 1 unit, balance is 9. So you add 9 to this P1, 32. So you can check the schedule length is same, 32 and 32, but number of preemptions are more, number of context switches are more. If you calculate the number of context switches, here I have 1, 2, 3, 4, and here I have context switches 1, 2, 3, 4, 5, 6, 7. Even though the number of context switches are more in the case of preemptive scheduling than in comparison to non-preemptive approach, why is it that the schedule length is same? Schedule length is 32 and 32 here. Schedule length is same because the value of scheduling overhead delta is 0. Had the value of delta been greater than 0, then perhaps I would have got more schedule length for preemptive approach of priority based scheduling. So boys and girls, this is the approach of priority based scheduling. Essentially, its performance will be similar to that of SJF. Like if I keep on getting high priority processes, we will be subjected to suffer from the problem of starvation. And to overcome the problem of starvation, we can go for similar technique like aging algorithm, as we saw earlier, aging algorithm. That means as the time progresses, increase the priority of the processes so that over a period of time, low priority processes would become high priority. That is called aging algorithm. And with that approach, you can control, you can bring down the problem of starvation to a significant extent. Okay. So this is the approach of priority based scheduling. Now the question is, this is an interesting aspect. This is there in the 𝐂𝐤𝐴LMIN textbook, 9th edition and 10th edition. The hybrid approach or integrated approach, that means can we integrate multiple scheduling techniques? Like here we are talking about integration of priority and round robin. Is there any possibility of combining these two algorithms? Do remember that Round robin is non-priority based, and priority is of course based on the level of importance of the process. So round robin is non-priority based. So how can we combine with priority based? That is integrated scheduling. I call it integrated in my own terminology. So we will try to understand this approach. Please see here on board. What is a basic working paradigm of integrated algorithm priority along with round robin? Run the process with the highest priority. Look at this. So first we are favoring the process having highest priority. But when the processes are having the same priority, that means if I have multiple processes with the same priority, then we are going to apply round robin. So round robin will essentially be applied when I have multiple processes with the same priority. So how does it work? It's very simple. Let's take this data set. Boys and girls, please observe this data set. Observe this data set. Okay. These are the processes, their burst times and priority, and I will follow the same convention what is there in the textbook. This is the highest priority and this is the lowest priority. This is the lowest priority. And these are the burst times. And the time quantum to be used for round robin scheduler is 2 units here. So how are we going to integrate this? So before I show the Gantt chart, I would like you to basically pen down the Gantt chart, draw the Gantt chart, and then you can compare with my answer. Okay. Simply you should pause the video and then you can basically try to check what you have done is right or wrong along with my approach. So here you can see, this is an example taken from Galvin textbook. Alright. So the arrival times are 0. So essentially which process should start first? First P4 should start because that is the highest priority. And there is no other process with the same priority one. So P4 is going to run and complete non-preemptively for 7 units. After that, we have the next highest priority. Look at this. The next highest priority is 2 and 2. That means I have multiple processes. So what are we going to do? For these two processes with burst times of 5 and 8, we are going to apply time quantum of 2 units. P2, P3, P2, P3, P2, P3, like that they run for 2 units, round robin. And once these two processes get completed, then again we go for the next highest priority, which is 3 and 3. So among these processes, P1 and P5 again, P4 with burst times of 4 and 3, we'll apply round robin with time quantum of 2 units. So finally, eventually, how does the diagram look like? You can see the diagram here. Check the diagram here. So first, as I said, P4 is going to run because that's the highest priority for all 7 units. After that, P2 and P3 are having the same priority, so they are going to take chunks of 2 units. 2, 2, 2, 2, like that, 7 to 9, 9 to 11, 11 to 13, till both P2 and P3 complete here. P3 has got completed, P2 has got completed here, P2. Check, P2 has got completed because P2's burst time is 5 units, so 2 plus 1, 5 units it completed. And thereafter I have remaining burst time of P3 only for 4 units because P3's burst time is 8 and P3 has run for 4, so balance is 4, so it directly run for 4 units and complete. And after that, I have P1 and P5, so they are going to oscillate using round robin with time quantum of 2 units until they complete. So this is, boys and girls, a simple algorithm which you can expect in the GATE exam or any other competitive exam, and this is a new approach which was not there in the earlier editions of Galvin. In the latest editions of Galvin, this approach is there. So I would like you to basically get well familiarized with this because it's a potential question in most of the competitive exam, how we can integrate priority with round robin. Okay. And the last scheduling technique is nothing but multi-level queue scheduling, multi-level scheduling. So I would basically say that essentially the scheduling algorithm that we presented so far, starting with first come first serve, shortest of first, shortest remaining time first, round robin, priority, etc., they are all based on single ready queue system. In the single ready queue, we will inject all types and categories of processes. Now, when I say all types and categories of processes, I mean to say those which are like operating system process, foreground, background, backup, and then in fact you can have your own categorization also. So categories, all categories of the processes, all the types of processes are injected into a single ready queue. Having a single ready queue with all categories and types of processes will impose certain restrictions, will create some problems. Like if I want to select a particular process in a particular category, then a lot of filtration time is needed, lot of filtration time, lot of searching time. That is one issue, one challenge. The other challenge is having a single ready queue implies I can apply only one scheduler on all categories and types of processes. So if you want a flexibility wherein I should use different schedulers, different scheduling techniques on different types or categories of processes, then what are we going to do? We should have multiple queues. Instead of having a single ready queue, let there be multiple ready queues, one ready queue for each type or category of process. So every process, every category, every type of process will have its own ready queue. Will have its own ready queue. First ready queue OS process, second ready queue interactive, third foreground, background, backup, and so on. So that whenever a new process arrives, we are going to find out what type or category of process is it, and accordingly we'll place the process in the respective queue so that we can avoid the searching time or filtration time. So that is the basic notion, basic ideology of multi-queue. So ready queue consists of multiple queues, that's what we are saying. So multi-level queue scheduler defined with the following parameters. How many queues are we going to have depending on the types or categories of process? What scheduling algorithms are going to be used for each queue? That's what I said. So method used to determine which queue a process will enter when that process needs service. And scheduling among the queues, these are the important challenges to be observed, to be followed in the multi-level queue scheduler. Okay. So with priority scheduling, right, have separate queues for each priority. So this for highest priority, then the next highest priority, next highest priority. So this division into multi-level queues is based on priorities, based on priority, highest priority, next highest priority, next highest, and so on. So accordingly, when a process arrives, we will inspect what is the priority of it, or we'll create the assign the priority and accordingly inject into it. So initially we start with here, or all processes can be injected here, and then like that they slowly descend. So this simple multi-level queue scheduling. Okay. So with priority scheduling, have separate queues for each priority, schedule the process in the highest priority queue. So I will schedule the processes from the next queue only when the top queue is empty, naturally because it is the highest priority. So essentially the drawback of this approach of multi-level queue scheduler is the processes which are there in low-level queues will be subjected to suffer from the problem of starvation. Naturally, starvation will happen to the processes in the low-level queues. So if you don't want the problem of starvation, or if you want to bring down the level of starvation, control the problem of starvation to a certain extent, we can add a concept in multi-level queue scheduler which is called feedback, multi-level feedback queue. So what is the basic ideology of multi-level feedback? Please have a look here. So this is again the same thing like highest priority based on categories of processes like real-time processes, system processes, interactive process, batch process. These again categorization based on priority, which we have suffered from problem of starvation. So if you don't want starvation, as I said, you are going to use the philosophy of what I call feedback. Look at this. We are going to add a concept called feedback into multi-level queue. What is this feedback? Let's see. That means in this multi-level feedback system, the processes will have the flexibility of moving between the queues, various queues. So the parameters which are going to define the multi-level feedback mechanism are as follows. How many queues you have? What is the scheduling algorithm for each queue? Method used to determine when to upgrade a process from low level to high level to low level. Method used to determine when to demote a process. Method used to determine which queue a process will enter when that process needs service. And aging can be implemented using feedback queue, as I'm going to show you here, something like this. So essentially how feedback mechanism will control the problem of starvation, you can have a look at it. So what happens is, this is a feedback concept. The process is getting preempted from top level queue and going into next level queue, depriving the priority, decreasing the priority. So all new processes, boys and girls, all new processes will enter into the first queue, where I'm going to use, for example, round robin with a time quantum of some values, say 8. Every process will be given a uniform chance to run for 8 units of time. Within that 8 units, if it complete well and good, it will leave. But in case if it needs time more than 8, then we are going to demote the process into the next level queue feedback, where I will subject the process to schedule on CPU only when the first queue is empty. When the first queue is empty, I come here, where I will give more time quantum to the process. Earlier I gave 8 units, now I'm going to give 16 units. Earlier 8, now 16, total 24. If it complete within 24 units, now it will leave the system. If it doesn't complete within 24 units, again if it needs more time, means its priority is low, so it will get demoted to the next level queue. Now, this being the last level queue, I have to make sure that the process has to complete its execution. So obviously I don't have any choice other than using the natural non-preemptive scheduler, which would ensure the completion of the process, and that is nothing but first come first serve. So last level in the multi-level feedback mechanism, last level queue in the multi-level feedback mechanism would use FCFS to make sure the completion of the process. So this is the basic ideology of the concept. So let's read the point. The Q0 is round robin with time quantum, and like that. A new process enters Q0, which is served in with round robin. When it gains CPU, the process gets 8 milliseconds. If it does not finish in 8 milliseconds, the process is moved to Q1. At Q1, job is again served in round robin and receives 16. So like that, it goes on and complete in Q2. So boys and girls, that completes the CPU scheduling chapter, right? From the academic perspective, that means the scheduling algorithm which I discussed in all these videos, this is the 5th video in scheduling, should basically help you understand all the scheduling algorithms to the core extent, and this should also help you in preparing for your semester exams in the course of operating system with the topic of CPU scheduling. Now it's time, as I said, that this will also basically help you for building your understanding with regard to competitive exams like GATE and others. So just to give you a small example how the typical questions are generally asked, I have brought some basic questions from PYQs of various exams to like GATE and BARC and ISRO, so that you can get an idea as to what type of questions are asked and to what level you are supposed to basically prepare for solving problems. So this is a very simple question of GATE PYQ. This is a GATE PYQ. Okay, I'm not writing the year in which it was asked, but essentially this is a PYQ. It's based on round robin. It's a very simple question. Consider a set of 4 processes, namely A, B, C, D, arriving in the order at time 0 plus. Now what does 0 plus mean? Just immediately after 0, that is the meaning of 0 plus. Just when you start the time after 0. The burst time requirements of the processes are 4, 1, 8, 1 respectively. Using round robin scheduling with time quantum of 1 unit, what is the completion time of process A? You can simply make a Gantt chart and try to complete the process A and find out what is the completion time. So let's make a trial. So the processes are in the order A, B, C, D in the ready queue. So starting at 0, we are going to run A followed by B followed by C followed by D, each for 1 unit. So therefore 1, 2, 3, 4. Now in the first round, you can see here 4, 1, 8, 1 means the process B and D got completed. Their burst time requirements are 1 and 1. So essentially I have only processes P1 and P3, sorry, that is A and C. So they will alternate till they complete A, C, then again A, then again C, then again A, then again C, like that it goes. I want the completion time of process A, so process A need 4 units. Process A has run for 1 unit here, 2 units here, 3 units here, 4 units. So boys and girls, essentially, this is the completion time, this is the completion time of process A. This is the completion time of process A. So mark the value 5. Every process run for 1 unit. So what is the answer? The answer is 9. As simple as that. The completion time of process A is 9. So it's a very, very simple numerical answer type question. We can say NAT question. So the completion time of A is 9. Next. Look at this. A very simple question on shortest remaining time first. Consider the following processes with arrival time and the length of CPU burst given in millisecond. The type of algorithm to be used is preemptive shortest remaining time first. Even though SRTF by default is preemptive, but explicitly again it is mentioned in the question. They are asking for this data set, what is the average turnaround time of these processes? A very, very direct question. So if you have followed the working mechanics of the question, working mechanism of SRTF, then it's a matter of only preparing the Gantt chart and solving the question, getting the values. So when I prepare the Gantt chart, it looks something like this. So let's start. This time 0. So 0 we have P1, look at this, 0 we have P1. So P1 is P1 is going to run for 3 units because the next process arrives at time 3. Its balance is how much? Balance is 7. New process is 6. 6 is less than 7. So naturally preemption in favor of P2. How long P2 is going to run? P2 is going to run from 3 to 7, next arrival. And by this it has run 4 units. So its balance is 2. And new process at time 7 is having burst time of 1 and that is lesser than 2. So therefore preempt in favor of P3. And P3 has a burst time of only 1 unit. It completes at time 8. So P3 is over. Now no new process is going to come. At time 8 I have this 7, 2 and 3. So obviously who is going to run? P2 is going to run. P2 need balance of 2 units, so it is going to finish at time 10. So P2 is over. Then followed by whom? P4. P4 is 3 and is 7. So P4 need 3 units of time. It is going to run till time 13 and complete. And lastly, P1 is balance of 7. So 20 it completes. That's it. Once you prepare the Gantt chart, it's a matter of computing the turnaround times. So if you compute the average turnaround time using the formula which we have seen, so average turnaround time of P1. P1 completed at 20, arrived at 0, so therefore 20 is arrived turnaround time of P1. P2 completes at 10, arrives at 3, so 10 to 3, difference is 7, right? And P3 complete at 8, arrives at 7, so 7 to 8, 8 to 7 means 1 unit, is it not? P3. And P4, look at this, P4 completed at 13, arrives at 8, so 8 to 13 means basically 5, so its turnaround time is 5. So this is total turnaround time 27, 28, 28 plus 5, 33. Is it not? 33. 33 divided by number of processes 4. So it becomes 4 is the 32 and then 8.25. Something like this. So that's how we compute the average turnaround time. Hope I have not made any computational mistake. You can check just in case. If there is a computation mistake, you can indicate to me in the comment. Okay. And that's a matter of, I mean, sometime we may make, just in case we observe there is any mistake, but Gantt chart is correct. Okay. So that's the point. So boys and girls, let's see another example. The sequence is also a gate PYQ, one of the old gate PYQs. The sequence, which sequence, that is 3 to 1, 2 1 3, 3 to 1, 1 2 3 and so on, is an optimal non-preemptive scheduling sequence for the following jobs, which leaves the CPU idle for dash units of time. The point of observation is, in this question there is no mention about the particular scheduling technique. It is only said that you are going to use non-preemptive approach of scheduling, like FCFS or shortest job first. They are non-preemptive. So how should we schedule so that we can get optimal schedule? What should be the optimal scheduling sequence? Now we need to work out by choices. Listen to this. These the sequence and these the idle time for every option. First option say that you are going to start with job 3. What is the arrival time of job 3? Job 3 arrives at time 1. And if you want to start with job 3 using future knowledge scheduling, it means minimum I should have idle time of 1, and that is what it says. So therefore, by keeping the processor idle for 1 unit of time, look at this. I am preparing the Gantt chart for option A. So 0 to 1 I am keeping it idle. And after that I am going to start with P3. P3 need 1 unit of time because non-preemptive. So it completes at time 2. Thereafter we are completing P2. Taking time of 5, so 2 plus 5, 7. And then thereafter we are taking P1, right? P1 needs the 9 units, so therefore 16. This is the Gantt chart for option A. For option A, this is a Gantt chart. Is it not? So this is possible schedule, this is possible, but is it optimal or not? We have to verify. We will check. Now the question is option B. If you want to start with job 2 first, then job 2 arrives at 0.6. So minimum I should have idle time of 0.6, but the option says 0. So that means this schedule is not at all possible. This schedule is not at all possible. Rule of elimination. Likewise, if you want to start with job 3 first, we said already minimum idle time is 1, but the option says 0. So therefore this schedule is also impossible. But the question is option D. Schedule in option D, is it possible? We are starting with job 1. We can start job 1 without idle time, but the option say, the choice say you can keep it idle for 5 units. So therefore, it is also possible. That means instead of starting at 0, I will keep my processor idle for 5 units. And then I will schedule P1 taking 9 units. So 5 plus 9, 14. Followed by P2 running for 5 units, 19. And finally P3 running for 1 unit, 20. So here the schedule length will come out to be 20, and here in option A the schedule length will come out to be 16. So obviously which is optimal? So option A is optimal because schedule length is less, means the average turnaround time, average waiting time will be less. So naturally among the options which are possible A and D, option A is optimal. Option A is optimal. So the correct answer for this will become A. Next, look at this. This is a question from the exercise of Galvin textbook. Exercise of Galvin. You can have a theoretical question like this on dynamic priorities. Consider a system using preemptive priority based scheduling with dynamically changing priorities. On its arrival, a process is assigned a priority of 0. So when the process arrives, its priority is 0. Okay? And running process priority increases at the rate of beta, and finally by priority of process in the ready queue. Ready queue, when the process is there in the ready queue, its priority increases at the rate of alpha. So alpha, beta and 0. By dynamically changing the values of alpha and beta, one can achieve different scheduling disciplines, different scheduling algorithms among the processes. So question is, what discipline will be followed for the following condition? So if you prepare a simple schematic view here, this is ready queue and this is the CPU. Alright, so please pay attention. When a new process arrives, P new, its priority is 0. And those processes which are there in the ready queue, Pi, Pj, Pk, their priority increases at the rate of alpha, and whichever process is running on CPU, boys and girls, whichever process is running on CPU, its priority increases at the rate of beta. Am I right? Yes. Check it. 0, alpha, beta. Now question is, if I have the condition that beta is greater than alpha, it means that running process will always have higher priority than the processes in ready queue. Beta is greater than alpha. Means processes in the ready queue will never preempt the running process. And then both of them are given to be greater than 0. Means new process will have priority 0. So any new process is coming, that also is not going to interrupt the running process, disturb the running process. Means whichever is the running process will always have highest priority and it's not going to get preempted. Means in whatever order I am scheduling a process, it will never get preempted. First process to get scheduled will complete, then second process will get complete, third process will get complete. Means essentially this is typically working like first come first serve. Whichever process gets scheduled first will get completed, then second, then third. So essentially when this condition is followed, the scheduling algorithm will behave like FCFS. The discipline will be FCFS. So that's how we have to argue. That's how we have to justify our claims and solve the problems. So these are some simple examples of the problems which I have taken typical questions to make you realize how are we supposed to prepare for competitive exams. Okay. So this is not a full-fledged exhaustive list of programs. This is just a sample set of questions which I have given. Basically, if you really want to prepare, you have to solve all PYQs and other competitive exams in order to gear up to take up such tests. So this is what I have for this session, and if you are really interested in taking up subscription career for your higher education, you need to write the GATE exam, and it is always desirable that when you write the GATE exam you should prepare with a competitive spirit, right? Because there are a lot of competition. So self preparation you can do it, no doubt, but if you are preparing with experience and erudite faculty who can teach you exactly what to learn, what to study, right? You can take subscription with our platform like GFG. So this is a QR code of GFG, and this is a QR code of my Telegram channel. This is my email ID. At any point of time, for any clarifications, you can revert to me through email or through Telegram channel, and seek clarifications with regard to any kind of academic advice related to studies, related to projects, mini projects, internships, right? Career aspects, anything you can feel free to contact me. So boys and girls, as I was saying, to get the details about the batches that are available for competitive exams of GATE, ISRO, NIC and others, you can scan and then take subscription. Okay. Thank you so much. In the next lecture, we'll start with the new topic on maybe threads and multi-threading or perhaps synchronization. Thank you.